you think a commercial process can work with chlorine filtration?
That's going to be a real big problem, but yes, there are commercial projects with chlorine, all right? I don't think it'll work with this, okay? The temperature's too high and you have a materials problem. You could do it if you lined it with aluminum, but as you know, those people who tried to do that and had the aluminum crack out of their reactors. We ran oxychlorination at Carbide for methane and ethylene. We used firewood, and it was under fairly severe conditions. So it can be done. It can be done. The oil companies aren't going to want to do it for a number of reasons. At lower temperature, easy. Ethylene oxides run with chloride. Go to 400 degrees, 500 degrees. Yes?
Union Carbide continues their work for another 10 years.
We're not commercializing the catalyst I talked about today. It could be that we would choose to do this in the future, but that decision certainly hasn't been made. We will continue research, and we are continuing research in methane coupling, yes. Our government contract has ended. Union Carbide made the decision that they would continue research. They're a little worried about some of the liaisons we have with other companies, and we will continue research on our own.
That's good news.
The final paper of this morning's session is contributed on the Morgantown Energy Technology Center facility supported by the United States Department of Energy. It's entitled Catalytic and Non-Catalytic Oxidative Coupling of Methane to C2 plus hydrocarbons. The speaker is Abolghasem Shamsi.
First, I'd like to define non-catalytic is, which I mean here that we didn't intentionally introduce catalysts, but I wouldn't guarantee there's no catalytic effect even when we don't introduce catalysts. I'd like to talk about the effect of temperature, pressure, and possibly resonance type on catalytic conversion of methane, and for comparison, some methane and ethylene to C2 plus hydrocarbons. Our objectives are to develop a process. This is a genetic objective, but the process has to be simple. The reason for that is most of the economic study shows you have to have very cheap gas and a high demand for fuel. Otherwise, you're not going to make it. Therefore, the cheap gas is far away from the market, and we have to be simple and economical process to do and produce cheap oil. To do that, we need first to make a catalyst, and we are going to be focusing mainly on preparation and testing of new catalysts for oxidative coupling of methane to C2 hydrocarbons. And we started with a broad objectives to do many things, but soon we found that it's too much work and less manpower. We decided to start and stop in halfway in the first two. The way most of you are aware of that already exists mobile process in New Zealand, which are using steam reforming and methanol synthesis and methanol to gasoline, which is three steps. And if we can reduce some of those steps, especially in the steam reforming step, we may produce oils cheaper in that process, hopefully. And the way we tend to do is to use only two stages. To first make olefin, and then use the established process, which is olefin to gasoline, which is already working in New Zealand. We originally started with the crosscut catalyst. The reason for that is the literature is a lot of information exists in the literature for complete combustion of hydrocarbons, especially in catalytic converters. And we said if we can get the information and go the opposite way, we may be able to make more ethane and ethylene. And it's very flexible. Is by changing the cathode for one element to other. If you use iron, chromium, or nickel or cobalt, you get a complete oxidation. If you go to platinum, manganese substitution structure the way we have, we produce about is a yield of about 20 to 20% C2 yield for oxidative coupling. We did X-ray diffraction, but not in detail to say that we know exactly all the alkali went into the structure. But we did look after and before reaction, we see still structures intact, and especially when the impurities stay not much different from before and after reaction. But what we did is we did a temperature programmed desorption of oxygen in these samples. What we found is, at least at this range, two types of oxygen exist, which at higher temperature we believe is the lattice oxygen, which we cannot even see the peak. This is up to 900, 950 degrees C. But there is another type of oxygen at lower temperature, which we think has to do with the combination of oxygen and alkali on the surface, which is not actually in the bulk of prospect. And this oxygen is mainly, we think, is responsible for complete oxidation. Which is interestingly, when this is at this range, after this range, or at this range, we get the highest C2 selectivity. Which, if we mentioned of Suka's latest paper, is the oxygen which is loosely associated with the surface is caused the deep oxidation, which means we have to go high temperature now to remove this loose oxygen, which is causing deep oxidation. We get the maximum C2 selectivity at this range. Now, what we did, we plot this temperature for a maximum C2 absorption versus C2 selectivity. We see a relatively nice correlation. The stronger the oxygen, and or better C2 selectivity we get for this type of catalyst. Another one, if we look back at the first slide, we saw the peaks were very broad, which means we really don't have a pure oxide with this oxygen is coming up. Which means that alkali, they're both in the, it has been substituted, and there are still extra on the surface, which contributed to that oxygen desorption. Now, another concern we had was, as Barbara mentioned, was the gas phase. The first study that we did, we tried to eliminate and fill all the extra dead space in the reactors and have a blank reactor and compare. And most of the conversion in the blank reactor was, we kept it at less than 1 to 2%. But later on, many reports came out that gas-phase reaction, most of these catalytic studies are gas-phase reaction, and we start to worry about it, and we try to find out more about what's happening. This test is, there's no catalyst introduced in this experiment. We see oxygen and methane conversion goes up drastically as we raise the temperature, even with no catalyst. But as we see here is CO is the major product. But if you look at different catalyst studies, they also sometimes they show the CO as a major product, which in all the catalysts that we tested, we didn't see CO. We see major product is CO2 when you choose catalyst. We believe the CO is the product which is formed in the gas phase. And another factor we did look into it was effect of pressure. that is we see similar activity, similar trend, which methane and oxygen conversion goes up as we raise the pressure. Again, we have CO is our major product. As we raise the pressure, CO concentration goes up, and in this case is formaldehyde, which we saw at the lower conversion and lower temperature, and C2 product goes, which means at higher pressure we're converting more C2 products into carbon dioxide, which this time we don't have any catalyst, is carbon monoxide. Now, we know the pressure is affecting contact time. We did a simple study. We injected argon and we raised the pressure. We see a linear correlation between increasing the pressure and contact time. We decided to look into contact time. We see a similar trend. As you raise the contact time, we increasingly convert the C2 and formaldehyde to CO, which we don't have. In this case, we still don't have any catalyst. In this, we try to compare ethane and methane. See, we are making ethane, and we're assuming ethane and ethylene is going to be a state there when we're raising that high temperature, we go to that high temperature. This is just for comparison. Some of the literature shows that if you have ethane in presence of methane, the reaction of ethane gets retarded to some extent. But still, if we compare the temperature, that we get 50% oxygen conversion. The temperature for ethane is almost 250 degrees below what you get 50% oxygen conversion for methane, which in this case shows if we are making ethane, we have to worry about they're going to react back even in the gas phase or on the surface of catalyst. Now, the next slide is going to compare ethylene, which is also see even lower temperature, about 50 to 40 degrees below than ethane, if we compare the 50% conversion for oxygen. We see about 40 to 50 degrees C, even lower than ethane. What is surprisingly in the ethylene case, the product is ethylene oxide, and the coke formation is large. You cannot run it at this type of conversion more than 2 hours because it can be blocked up hydrocarbons, and especially char. Even if you have 2 to 1 oxygen to ethylene is 2 to 1. At the presence of very high concentration of oxygen, your still coke formation is large, and we believe that when it's methane there supplying all the hydrogen, that's why we don't see much coke when we have methane. We believe that the mechanism possibly is completely different when you have methane and supply of hydrogen in the system. But this will give us some indication when we're forming methane. We're forming ethane and ethylene, we have to worry about to react both in the gas phase and in the surface of catalyst. At this point, we introduce one of our catalysts, which is lanthanum, which is lanthanum and manganese oxide, manganate. And this is we found it's pretty stable, and then we stick with it to compare it in the gas phase and surface. Now, if you look here, I put the contact time 2.4 seconds. The 2.4 second is roughly calculated based on the heated zone. It's not based on in the catalyst volume, because I assume that both happening in the gas phase and in the catalyst. Therefore, 2.4 seconds. The difference we see here, what we see is major product now is CO2 when we introduce the catalyst. We think that CO2 is forming in the surface of the catalyst. At contact time of 2.4 seconds, we have extra data space between the two between the catalyst, above and below the catalyst. As Barbara mentioned, earlier we decided to eliminate those data space and eliminate as much much as possible or minimize it, and then we have only the callus volume. And contact type is based only the callus volume now here. Now what we see is the trend is opposite one, the CO2 going down, which means at this lower temperature, almost, or we cannot say completely, most of the reaction happening on the surface. As we raise the temperature, we're increasing some gas-phase reaction, and CO2 going down, and the product of the gas-phase reaction, which is CO, is going up. And we try to test these callus under pressure. I should say that the pressure is not a high pressure. 3 atmosphere is not a pressure that to be concerned. But most of the fixed bed reactor can create that type of pressure. The reason for this is because there's a lot of empty reactor has been reported in literature, but one criticized the other one that is wrong. The reason for that, one of them is they don't control their back pressure and or front pressure. They don't monitor those pressure, which is even at this low pressure, it has a significant effect on methane and oxygen conversion. If we monitor carefully and then report them in the literature, and then we understand why our experiment is different than other labs. And what we found that even with a slight increase in pressure, we see significantly contribute to the oxygen conversion and also to methane conversion. At this low pressure, even we can see up to 30 to 38% methane conversion at that temperature. At the same time, it's contributing similar than residence type or temperature. We increase our CO2 concentration and lower our C2 as we raise the pressure. Now, in some studies suggest that if we go to lower temperature, we may be able, if we do anything at lower temperature, we may be able to reduce some of these gas-phase reactions and hopefully increase our C2 selectivity. Well, we did, we went one step lower in temperature. We see a similar effect also at lower temperature. If you even take our data point from here, as soon as we pass this concentration, is still increasing the pressure, but also at higher pressure we can see lower C2 selectivity, and we see higher oxygen and methane conversion. We conclude here that the pressure is going to be as opposite effect. We are not going to increase our C2 selectivity if we have any pressure in the system. It should be at atmospheric or lower pressure if you really want to get any C2 out of the process. Now to complete our result is we're reporting that methane to oxygen ratio is another factor that we have to be careful about. As we put more oxygen in the system, we get more carbon dioxide, and as shown in here, or shown here is the opposite way. If we raise more pressure, partial pressure of CH4 to oxygen, and then we see here is or CO2 again is the major product, and the C2 products reach a maximum to a certain. This is the better range to work with if you don't want to make a lot of CO2. Methane to oxygen ratio between 3 to 5. If you want to go lower, you sacrifice your conversion. You go put more methane, you sacrifice some of your conversion. If you go the other way, you make more CO2. It's good to stay between 3 to 5 is methane to oxygen ratio. Now to summarize this, saying that callus are effective and are contributing to overall reaction processes. We compare some of our earlier results, and we see in this case we prefer less oxygen under nitrogen in this case. In here, lanthanum manganate was preferred under oxygen atmosphere. And then as we add alkali metals, we found that you can increase your C2 selectivity and conversion like meth. And another factor is methane to oxygen ratio, that is shown in the next two plots. You can increase your C2 yield by increasing your oxygen in the system, but at the same time, you're making more CO2. You may increase your yield from 15 to 20 if you want to deal with more CO2. In that case, you get less methane conversion, but still you get a better selectivity. Therefore, you can, in the process, you have your choice, go to more oxygen and get a slightly better yield, or stick with the lower oxygen concentration and get lower yield, but at the same time making less CO2. Now, to conclude that is, we did prefer some stable perovskite type catalyst, and we tested, we get a yield of between 20 to 22% for C2s. And then we found that contact time, pressure, temperature, it has to be controlled very carefully if you want to compare or result to other labs. And from our temperature program desorption, we think that more loosely, oxygen are contributing to deep oxidation. And mainly CO2 is forming on the surface from the intermediate. Could be the radical, ethylene, and especially CO is going to CO2 on the catalyst. Thank you very much.
Well, I'm sure we have plenty of time for questions.
With regard to this matter of selectivity and conversion, I understand the newest answer to acid rain is going to be a lot of methane burned to replace high sulfur coal for power generation. Would it be possible to combine the production of ethylene with power generation so that selectivity wouldn't be quite so critical? In other words, what you lose on selectivity and conversion you pick up on. It'd be a new kind of combination process, but I wonder if the economics were cranked into it in that manner, whether it would look better. You follow me?
Well, I think a combination will be beneficial because you have more hydrogen-rich methane here and the oxygen deficient coal or any other source you're talking about. I think would be useful because you have oxygen-rich and nature separated, we put it together. Yes, you know.
Labinger at Caltech has said that ethylene oxidizes very rapidly. It goes to CO and CO2. And part of it is gas-phase reaction and part of it occurs on the catalyst surface. Are you able to say from your studies how rapidly ethylene is oxidizing and whether addition of an alkali slows down at least the surface reaction?
From this study, we can say that ethane and ethylene goes to CO2 depending on the catalyst or not, is faster than methane. But how much methane is going to affect the oxidation, we don't know. We have at least some kind of, I want to do some label at ethylene and methane in the future, if time permits. That may conclude some of those questions, but I haven't seen any labeling in carbon-13 in the system, which tell us, I believe that hydrogen coming from methane is affecting the mechanism of ethylene oxidation because really we don't see much coking when you do partial oxidation of methane. Or if you do ethylene itself, as coking is a big problem, which means you get all the hydrogen from methane. It does affect the ethylene oxidation, definitely, but we don't know how much. Please be there. But if, as pure, we can see a very low temperature, you can oxidize ethylene.
all of this morning's speakers for very stimulating discussion.